In 2022, Italian radar specialist Filippo Biondi presented a provocative claim. New scanning technology had detected 8 massive cylindrical structures deep beneath the Giza plateau. The method behind this assertion is known as synthetic aperture radar, or SAR, Doppler tomography. The internet immediately seized on the raw data. Viral videos declared this as proof of advanced ancient technology and a kilometer-deep lost city. Meanwhile, the academic community pushed back hard. Mainstream archaeologists dismissed the findings as misinterpreted satellite noise, pointing to the immense scrutiny this physical site receives. To navigate between internet mythology and academic dismissal, we have to look past the rhetoric and objectively evaluate the raw data alongside the physical limits of the radar technology itself. We can do that by setting up a reality check. We will weigh the viral promises against the actual physics of SAR Doppler tomography. We are going to answer 5 specific questions about the satellite's footprint, the missing evidence at the site, how this compares to proven scanning methods, and the actual path to scientific validation. True archaeological breakthroughs rarely happen cleanly. They require a messy, expensive, and frustrating process of calibrating new scientific tools. Question 1. What exactly did the SAR satellite measure from space? A satellite passes over a 5 by 5 kilometer grid for 15-second intervals, scanning for microvibrations known as phonons. An algorithm translates those microvibrations into a 2-dimensional waveline, then mathematically inverts it to infer a 3-dimensional model of subsurface density. But this method carries a specific, well-documented flaw. It's called layover. Layover is essentially radar shadowing. It occurs when the highly sensitive vibration tracking gets confused by surface noise or overlapping signals. Because of layover, the raw data is incredibly vulnerable. Standard surface noise can easily be misinterpreted as massive underground structures. Question 2. Why didn't the scans clearly show the known pyramid chambers? This cross-section schematic highlights verified interior spaces, like Khufu's subterranean chamber, carved directly into the bedrock. The SAR data struggled to register these known voids. Because these chambers aren't anchored to the vibrating surface, they return weak or entirely missing signatures. If the technology currently fails to reliably resolve known shallow chambers, we have to heavily discount its credibility regarding unverified kilometer-deep anomalies. Question 3. How does this experimental radar compare to the muon scans that successfully found the Big Void in the Great Pyramid in 2017? Muon tomography relies on cosmic ray absorption rather than vibration. It is a peer-reviewed and academically accepted method. The trade-offs center on operational costs and speed. SAR offers rapid 15-second wide-area scans from orbit. Muon scanning requires months of physical sensor placement inside dark, restrictive pyramid corridors. SAR is vastly faster and cheaper for wide-area targeting, but it currently lacks the proven accuracy of muon scans needed to deliver definitive archaeological proof. Question 4. If the Giza data is so noisy, why do Biondi's own proof-of-concept scans look so much better? The algorithm was successfully tested on massive modern infrastructure, like the Gran Sasso Physics Lab and the Gotthard Base Tunnel in the Swiss Alps. By applying a different focusing procedure to these modern sites, the scans produced crystal-clear visual representations of tunnels and turbine structures. This confirms that while the SAR method is functional, the Giza results are currently limited by noise and the complexities of scanning ancient limestone, a sharp contrast to the clear data from modern sites. Question 5. What is actually required to prove these deep structures exist? The immediate hurdle is technological. Processing the heavy mathematics required to clean the data and remove the vertical stripe noise demands massive arrays of GPUs. The next hurdle is scientific. The team must execute control sample scans on empty, featureless bedrock. You have to establish a baseline of what nothing looks like before you can prove something is there. Proving this theory requires millions in private funding and years of heavy data processing. We face a long period of digital uncertainty before anyone picks up a physical shovel. This chart maps out exactly where SAR Doppler tomography currently sits in the hierarchy of archaeological truth. In the bottom right, we have traditional physical excavation, highly conventional, highly verified. In the top right, muon tomography, highly experimental, but heavily verified. And in the top left, the Giza SAR scans, highly experimental and currently unverified. Treating preliminary, uncalibrated radar scans as absolute fact halts the slow, iterative scientific process actually required to validate them. If you follow alternative history, you need to step back. Do not use this noisy radar data as definitive proof of a lost city. Use it as a map of unverified targets. If you are a skeptic, do not throw the baby out with the bathwater. The Giza scans are flawed, but the technology works on modern infrastructure and represents a vital new analytical frontier. And if you are evaluating the technology, the real story here is computational physics. The next major breakthrough won't come from a trench, but from funding the GPU mainframes needed to process this data. The Giza anomaly provides a high-stakes testing ground for this new method of observation. It demonstrates that mapping the unseen layers of history will require years of calibration and significant computational power.